Okay, so this is where we were. So I work on an example for you, illustrating that the recursive formula for calculating the for computing the global encoding vectors actually works as we hope. Now, here in this picture, I show you in this figure I show you the same network, except that the all the local encoding coefficients are regarded as an indeterminate. So it means that I don't assign zeros and ones to them, but I just leave them open. So each one of them can be either 0 or 1. Okay. So if you start with assuming that this is a NQPR, using the local these are the local encoding coefficients, and then you operate these on the input global encoding vectors, and you can work things out like this, and then with this being S and T, you can work this out, work out these things. Okay, so eventually everything is in terms of these indeterminates, which are the local encoding coefficients. Now I would like to define something called linear multicast for you. So linear multicast is a omega dimensional linear network code such that the dimension of VT, okay, I'm going to tell you what VT is. Okay, I should talk about this first. So this is T, and these are the input channels to T, and VT is the this vector space spanned by all the input global encoding vectors. Okay. So so at the end of the day, what you have is that so X is the input, and then you multiply X to VT. X is a row vector and VT is a matrix, and these are precisely the symbols that you receive on the input channels to the signal. Okay. So it doesn't actually, we don't distinguish a signal or a non-signal. We just T can be any non-source node. So dimension VT equals omega means that this linear transformation associated with input channels is full rank. If dimension of VT is equal to omega, then based on the symbols that you receive on the input channel, you would be able to invert the matrix and compute the source vector X accordingly. So a omega dimensional linear network qualifies as a linear multicast if for every non-source node T with max flow T at least equal to omega, the dimension of VT is exactly equal to omega, which means that for any node, as long as there is enough max flow from the source node S to that node T, then you would be able to decode the message vector. So this is a desirable property of a linear network code, and we call such a linear network code a linear multicast, because it can multicast the source message to every non-source node such that the max flow is sufficient. Okay, now coming back to this example here, okay, with all the local encoding coefficients being indeterminates. So the problem that we are facing is the following. Now in this network, there are 3 nodes that has max flow equal to 2. So this node has max flow equal to max flow equal to 2 because there's one path here and another path here. Right? These edge destroying paths. And this node is also has a max flow equal to 2 because this one. And here, same thing. It's one path and another path. So we only need to design the network code such that node W, node Y, and node Z can recover the the message. Now, to do this, we have to resort to linear algebra. So basically, what we need to consider is that so for node W, the associated vector input, the global encoding vectors for the inputs are n, this vector and this vector. So what we do is that we put this these two vectors into a column. These two column vectors into a matrix, right? QU and RU, and then so this is a 2x2 matrix, and we require the determinant of this is not equal to 0. Okay. The same thing, we puts these two column vectors together to form a 2x2 matrix, and we require the corresponding determinant to be non-zero. And same, and again, we put this vector and this these two vectors together to form a 2x2 matrix, and we require the determinant to be non-zero. Now, the problem that we are trying to solve is to assign these determinants to either 0 or 1, such that all these three determinants are non-zero. So that's the problem that we are trying to work out. Okay, so the three. Let me show you the diagram again and the picture again. So we are focusing on this. This is W, and this is Y and Z. Okay. So then, as I mentioned, this is just to write down the what I said more formally. So for node W, we want this global encoding vector to be and this global encoding vector to be linear independent, or the determinant is equal to not equal to 0 when you put them together as a 2x2 matrix. The same thing for these two. Okay, these two, and then for these two, and then you just based on what is being worked out here, you just work out the determinant. Okay, this one is NSRU minus PSQU, right? So this is SU NR minus PQ. Right? So this is the and you require this to be non-zero. Now, in order for this to be non-zero, S needs to be non-zero, U needs to be non-zero, and NR minus PQ needs to be non-zero. So this is just what I put down here. Now the linear independence of these two vectors corresponds to these being non-zero, and you can work out for the other two nodes accordingly. Okay, so you have this being non-zero, this being non-zero. Now as long as you can find assignments of the indeterminates such that all these conditions are satisfied, then you would be able to have a linear network code such that W can decode, Y can decode, and Z can decode. And this example that we have shown here, either this or this, okay, is such a case. So to obtain this code, okay, which works with such that W, Y, and Z all can decode, we just set NRS TU, W, X, Y, Z to be 1 and P and Q to be 0. Okay, that's what we have done. Okay. Except that I'm explaining this from in a more general setting. Okay, now now one thing is that in order for the network code to be able to decode, we need to know the global encoding kernels ahead of time. Okay? If they're not known ahead of time, they because these global encoding kernels tell you what linear transformation that the symbol you receive has gone through. If they are not known ahead of time, they can actually be delivered on the fly with an overhead. So the idea is that we use the same network code n times where n is greater than omega, and we pay a premium for that. We use the first omega time slot to send a dummy message. I'm going to explain to you in an example. So it's like this. So we use the network n times where n is greater than omega. So we use omega of these to send a dummy message, and the real messages that we send are x1, x2 up to xn minus omega. Okay. So up here, we form these are the dummy messages. In fact, when they are put together, they form an identity matrix. So what it means is that the first dummy message is we send is 1 0 0 something. Okay, and then 0 1 0 0 like this. Now this being the with this being the identity matrix, when you multiply this transfer matrix, okay, for the receiving node, so this f in t is this. So there's t and okay. So f in t is just the matrix formed by the global encoding vectors of these input channels. All right. So if you send an identity matrix through, then what you multiply this to fnt, you get fnt, right? And for the other unknown messages, what you get is x1 of f in t, f2 of x in t, and so on and so forth. Now, because you send a known matrix, which for convenience sake, we can assume that this is the identity matrix. In reality, it can be any invertible matrix. Then you actually can receive f in t. F in t is not known ahead of time. Okay, because for example, you can use this in a network with an unknown topology. You don't know what linear transformation the symbols have gone through, but you can learn the linear transformation by sending the identity matrix to start with. It's just like a pilot. Okay, and then once you have learned f in t, and as long as f in t is invertible, then you can by receiving x1 times f in t, you would be able to recover x1, so on and so forth. So this is the main idea of how you can deliver the global encoding vectors on the fly by paying a premium. Now here I would like to talk about existence and construction. Oh, I'm sorry, the animation here does not show up. So let me do it on the other computer. I'll stop sharing this. Okay. So can you see my screen?
Yes.
Yes, very good. Okay. So the oh, actually it's okay. I don't need this for the time being. So let me go back to my iPad. Okay. All right. So I'll skip the some of this discussion. The only thing that I want to say is that in order to be able to construct a linear multicast, you need a sufficiently large field to do the job. It's very much like if you're familiar with classical algebraic coding theory, in order to construct a random number matrix such that you would have sufficient linearity, among the columns of the matrix, you need a sufficiently large field. You cannot, if the field is too small, you cannot construct a random number matrix of the suitable of the desired size. So similar to that flavor. Okay, so here's another lemma which I won't get into the details, but basically it says the following. Now we let a non-zero polynomial with indeterminate 0 c top to zn, okay, and the with coefficients in the finite field. Now, if the finite field is sufficiently large, in fact, specifically, if the size of f is greater than the degree of g in every one of these indeterminates, then it is possible to assign values to these indeterminates, to assign a1 to z1, a2 to z2, so on and so forth, such that the polynomial evaluates to a non-zero value. So I'm not going to get into this, but the essential thing is that if you are given a finite polynomial, then as long as the field size is sufficiently large, you can always evaluate the polynomial to a non-zero value in the finite field. Okay, now here I'm going to prove for you the existence of a linear multicast. There are different approaches for doing that, but I find that the simplest way is the way proposed by first used by Curtin Medard. Okay, which and this result says that as long as you use a sufficiently large finite field, then you can always construct a linear multicast. Okay, so I'm going to use the example of the butterfly network to explain to you how it works. Now the okay, so we have the butterfly network like this. Okay, so we are focusing on these three nodes. Okay, and so W, Y, and Z. Okay, we let L, W, L, Y, and L, Z be the matrices of the global encoding kernels received at nodes W, Y, and Z, respectively. So these are LW is formed by putting this one together to form a 2x2 matrix, and LY here is is a matrix formed by putting this vector with this vector, and LZ L of C is to put this vector and this vector together to form 2x2 matrix. Okay, so but clearly, as explained before, we want all these three matrices to be invertible, or equivalently, their determinants are not equal to 0. Now, so now we want to ensure that each of these three determinants are non-zero in one go. So what we do is that we multiply these three determinants together, and because everything is in terms of these indeterminates, these three determinants, no matter how complicated they are, is simply a polynomial in the determinants. Now, in this case, we can see from this figure that these actually are not the zero. These determinants are not the zero, polynomial, because you multiply this by this, you multiply things out. They are not zero. Okay. Now, so according to the lemma I just mentioned to you, as long as the field size is sufficiently large, then you can always find assignments for these indeterminates such that this is evaluated to a non-zero value. Now, if this is evaluated to a non-zero value, okay, for some assignment of the indeterminates, where each assignment corresponds to a linear network code. So if you find an assignment of these indeterminates to evaluate this to a non-zero value, then it means that each of these determinants are evaluated to a non-zero value. Because if one of them is zero, then the product must be equal to zero. Okay, so now we by eyeballing all these global encoding vectors, we can see right away that all the three corresponding determinants are not the zero polynomial. So in this case, it is indeed possible to construct a linear multicast on the butterfly network. Okay. So, but in general, now this is a specific example, and I show that it can be done. But how can you prove the theorem in general? Now, here the claim is that okay, let me see. Now, in general, we are less. Okay, yes. In general, we are talking about just any node T, and in node T in network such that max flow T is greater than or equal to omega. Okay. Now, here I claim, this is a very important claim. I claim that in the network for any T such that the max flow is greater than or equal to omega, the associated determinant, this is the LT is the matrix formed by putting all these input global encoding kernel at node T together to form a matrix. And I claim that as long as max flow of T is at least equal to omega, then this determinant is not the zero polynomial. So how do we see that? Now the main idea here is that we can if max flow T is greater than or equal to omega, then we can find omega edge disjoint paths from S to T, right? And if there exist omega such paths, we actually can set well, we can simply route the symbols through, right? We have omega symbols, and we can actually route these symbols through, right? Now, routing, as I mentioned, routing is a special case of network coding. Now, specifically, what I'm saying is that you can actually set the local encoding coefficients for network code that mimics the routing mechanism. Now, if you set all these local encoding coefficients to mimic the routing of omega symbols from S to T, then what you receive at T would be the identity matrix. So in this case, for the T, Okay, and then you have a omega of these symbols coming through uncoded. Then in that case, LT with this particular assignment of the indeterminates would be equal to the identity matrix. Now, in that case, the determinant of LT would be equal to 1 because the determinant of the identity matrix is always equal to 1 for a specific assignment of the indeterminates. Now, because it is because for this particular assignment of the indeterminates, you can evaluate the determinant of LT to 1. It implies that LT is not the zero polynomial. If it is the zero polynomial, then no matter how you assign the indeterminates, you cannot evaluate the polynomial to 1. So this shows that for any node T such that the max flow is at least greater than at least equal to omega, then the associated determinant of that node is not the zero polynomial. Then what you do is that you in the next step, what you do is that you just form a gigantic. So each one of these determinant of LT is a polynomial, and then you form this gigantic polynomial by taking the product of all these determinants for all T, such that the max flow T is greater than or equal to omega. Okay. Because each one of these determinants is not the zero polynomial, this gigantic polynomial that you form by taking this product is again not a zero polynomial, and therefore for sufficiently large base field, it can be very large, but we don't care at this point. We just care about whether there exists a linear multicast. So you take a sufficiently large base field so that you can evaluate this this gigantic polynomial to be non-zero, and this implies that the evaluation of each individual determinant is also non-zero. Okay, and this in turn guarantee that at each such node T, decoding is possible. Now, so I've shown you how we can show I've explained to you how we can show the existence of the of a linear multicast. However, finding such a linear multicast could be computationally very expensive. Okay? If you use this approach, then the computation required is not polynomial time. So next, I'm going to show you an efficient way of constructing a linear multicast. Oh, okay. Before I talk about that, I just want to mention that if you choose a very large finite field F, then by choosing the local encoding coefficients randomly from the finite field, then most likely the linear null code is a linear multicast, and that which can be decoded. Okay. And the good thing about random linear null coding is that you don't need to know the network topology at ahead of time, as long as you use a large finite field, and every node is constructing a random code, a random linear code locally. Then most likely the other end would be able to decode. So this is a very nice property of random linear null coding. Okay, so I'll skip this. Okay, now let me turn to Jaggi-Sanders algorithm, which is a polynomial time algorithm for constructing a linear multicast. And the required field size actually is not big. You only need to use the finite field with size larger than or equal to eta, where eta is the number of sync nodes. Sync nodes means that you, in general, you can make all the nodes with max flow grid and or equal to omega as signals, but you can also have the option of choosing a subset of these nodes as signals. You can you don't have to use all of them as signals. In that case, you can reduce the requirement on the field size. Okay, now here's the main ideas of the Jenkins-Sanders algorithm. So so our problem is to multicast a message with omega symbols. So as before, we install omega imaginary channels at the source node S, forming in S, and we identify a flow of omega edge disjoint paths from in S to each signal. Okay, and then we assign global encoding vectors from upstream to downstream. Okay, I'm going to show you by an example. It's a little bit abstract at this point. So initially, the global encoding vectors are the at the source node are the standard basis, as I explained, and then recursively we will assign the assign the global encoding vectors. So the main thing is that we extend the flows from in S to all the signals while maintaining the linear independence of the global encoding vectors at the flow fronts simultaneously. Okay, you understand what I mean by flow fronts in an example. Okay, so I think I need to switch to my other computer for the animation. So you can see my screen?
Yes.
Okay, good. Okay. Yeah, I was presenting on a PDF file on my iPad so that I can write on it, but now I need the animation.
Yeah.
Okay, so so you see that from the source node to the sink node on the left-hand side, we have two paths because the max flow is equal to 2. So remember the pattern of this of these two paths in red, and then similarly we have a the max flow from the source node to the sink node on the right-hand side. Then maybe this one, okay, also has a max flow equal to 2. So that's why there are two edge disjoint paths. Okay. So what we do is that we are going to extend. So we start for the red pair of paths. They're both here. Okay. So the red one is the left imaginary channel, and the right one is the right imaginary channel. And then we eventually are going to extend these along the two paths that I showed to you, okay, like this. And the same thing for the yellow one. I'm going to extend it to here. Okay, so we assign the standard basis to the imaginary channels, and then we consider. Okay, now this is called this red edge and this red edge. Now this red edge is in fact equal to this imaginary channel, and this red edge is equal to this imaginary channel. Now this red edge is called let's see, what's that? It's called the flow fronts. The flow is initially here, but eventually the flow will go down along the paths that I've shown you. Okay? So the red flow front is these two channels, and the two vectors assigned to them are linearly independent. And same thing, for the yellow, this is a yellow flow front where where this yellow edge is assigned to this left imaginary channel, and this yellow edge is assigned to this imaginary channel. So for the yellow flow front, again, to start with, they are linearly independent. So now we consider assigning the global encoding vector of this edge. Now, if you consider this edge, you extend this red path to here, and you also extend the yellow path to here. Okay. Now, so right here, this edge here and this edge here forms the red flow front, and this edge, this yellow edge and this yellow edge forms the yellow flow front. So what we can do is to assign the vector 1, 0, okay, to this edge. Now this is a valid assignment because the vector that you assign to this edge here must be a linear combination of the input global encoding vectors. All right. So what we do is that we, basically this is equal to 1 multiplied by this plus 0 multiplied by this. So now we check whether the red flow front is can maintain its independence. Okay. So this and this, they're independent, and the yellow flow front, yes, again, they are linearly independent. So same thing, you assign, you extend the yellow, this yellow path to here, and you extend this red part to here, and you extend the yellow part to here. So here and then we assign 0, 1 to this edge. And again, this is valid because it's equal to 0 times this plus 1 times this. And then we now check the independence of the flow front. We first check the red flow front. So 1, 0 and 0, 1, they're independent. And for the yellow one, no, 1, 0 and 0, 1, again, they're independent. So you carry on, keep doing it like this. Okay. All right, now we look at this this critical one. So at this point, and then we extend to this one, and then we assign this the global this column vector to this edge. We assign it to 1, 1. It is valid because it is equal to 1 times this and 1 times this. And now this edge and this edge forms the red flow front, and we check its independence, which is true. Where 1, 0 and 1, 1 are independent, and then the yellow flow front is this edge together with this edge, and again we check its linear independence. So again, it's linear independent. Okay. So you go on like this. You further consider assign this this edge and 1, 1, and then you assign this edge to 1, 1. And then, so now the red flow front is these two edges, and we check its linear independence, so it passes. And for the yellow flow front, we have these two edges, and again they are linearly independent. So this is the basic idea of the Jacobi-Sanders algorithm. Okay, so let me switch back to the other screen. Okay, so I'm not going to give you a formal proof of this, but I just want to illustrate to you the main idea. And as long as as mentioned, as long as you take a few sides with elements at least equal to eta, the number of signals that you desire, then you would be able to construct the code. Okay, so here I would like to draw a relation between network coding and algebraic coding. So now in a linear multicast, a message of k symbols, I deliberately use k instead of omega here in order to relate this to classical algebraic coding, because in the classical algebraic coding we talk about nk code. So here we in a linear multicast, a message of k symbols form from a base field F is generated as source node S, and a k-dimensional linear multicast has this property: any non-source node T can decode the message correctly if and only if the max flow is greater than or equal to k. Now, by the max flow bound, this is also a necessary condition for a node to decode, because if a node doesn't have enough max flow, then no matter how you design your code, you have no chance that you can decode at that node. Okay. So therefore, the tightness, we say that in this sense, we say that the tightness of the max flow bound is achieved, in fact, by a linear multicast, okay, which always exists for sufficient large base fields. So this is so much for a linear multicast. Now we turn our attention to a classical NK code, a linear block code, with minimum distance equal to d. So we regard this as a network code on a combination network, right? Now, because for a classical block code with minimum distance d, then the NK code can correct d-1 erasures. So the combination network that I'm talking about is this one. Okay, so here from the source node, there are n output channels, and then they are each connected to a node in the mid level. Okay. And then down here, there are n choose n minus d plus 1 nodes. So n choose n minus d plus 1 precisely is this. So this is n choose n minus d minus 1. So I mentioned that for a code with minimum distance equal to d, it can correct d-1 erasures. So so it means that as long as you can get hold of the n minus d minus 1 symbols of the code word, okay, so this is a code word of the n of the block code. As long as you can get hold of any n minus d minus 1 of them, you would be able to decode. So at the bottom level, we have n choose n minus d plus 1 nodes, where each one of them has access to a distinct subset of n minus d minus 1, n minus d plus 1 of these symbols, of the n symbols. Okay, so this is called a combination network. Now, in the combination network, for the nodes at the bottom, evidently the max flow is equal to n minus d plus 1, because so it's just this, right? So you have this number of edge disjoint paths, so the max flow at this node is equal to n minus d plus 1. Now you treat this as we regard this as a network coding problem. Okay, so it is a multicast problem with S, and you multicast to all these nodes at the bottom. And now by the max flow min cut bound, the number of symbols that you can multicast must be upper bounded by the max flow at each of these t, which is n minus d plus 1. Okay, or if you arrange the terms, you get d is less than or equal to n minus k plus 1. And this is precisely the singleton bound in classical algebraic coding theory. So you see that the singleton bound is indeed a special case of the max flow bound for network coding. And in MDS code, maximum distance separation code is a classical block code that achieves the tightness of the singleton bound. Now, in the context of network coding, since a linear multicast achieves tightness of the max flow bound, one can formally regard it as a network generalization of an MDS code. So this here, I just want to relate what we have learned, what I've taught about for linear network coding with the classical algebraic coding theory. Okay, the next I'm going to talk about applications of random linear network coding in a P2P network. So this is actually quite enlightening. Okay, what is a P2P network? I think most people know, but I just go through this very quickly. Now, client server is the traditional architecture for content distribution in a network, namely that the client contacts the server, and the server you download data from the server. However, if the number of clients is large, then this becomes very inefficient because the server cannot entertain so many clients at the same time. Now, P2P is a so-called new architecture, but actually it's not new, not that new anymore. Now, in which users who download a file also help disseminating it. It is extremely efficient for large-scale content distribution, and in fact, it is estimated that P2P traffic occupies something like 70% of the internet bandwidth. And I check on the internet that the BitTorrent is still the most popular P2P system. If I'm wrong, please let me know. Okay, so I'm going to discuss a random linear network coding put together by Microsoft research some 15 years ago. Okay, so it's called Avalanche. It's a prototype that uses random linear network coding for software update. Now, it was in fact one of the first applications or implementations of network coding, and it was further developed into a software package called Microsoft Secure Content Distribution that was used for software update. So a similar system has been built for a Chinese content distribution company called UC.com. And so how does Avalanche works? So the when a server or client uploads to a neighbor in a P2P network, it is a P2P network. It transmits a random linear combination of the blocks it possesses. So I have received a number of blocks from my neighbors, and then when I upload to my neighbor, I take a random linear combination of whatever I have, instead of transmitting to them one of the blocks in my possession. So each transmitted block is some linear combination of the original blocks of the seed file, and download is complete if enough linearly independent network linearly independent blocks have been received, and decoding can be done accordingly. Okay, so here comes a very interesting question. Now, if you look at the butterfly network, at this node here where network coding is performed, you need to synchronize the two input bits B1 and B2. Okay, and so you need to wait until both of them have arrived before you can do the encoding. But in the Avalanche system, you don't seem to have to do it. When you are requested to transmit something, you just take a linear combination of whatever you have in your possession, and then you transmit. Okay? You don't have to wait for anything. So the curious thing is that what exactly is Avalanche doing? Okay? Is it doing the usual kind of network coding, or is it doing something else? Okay. So it turns out that the correct way to understand the Avalanche system is through a time parameterized graph. Now, suppose we in this P2P system, we have one server, and then we have 3 clients A, B, and C. Okay, and then let's assume that for the purpose of modeling, it takes one time delay to transmit to the next to the neighbor. Okay, so in this case, a server sends 2 blocks of symbols to client A and takes a one-time slot. So in this time parameterized graph, the x-axis is the time axis, t equals 0, t equals 1, t equals 2, t equals 3. And so this is server at t equals 0, the server at t equals 1, so on and so forth. So what this edge means is that at time 0, the server sends 2 blocks to client A, and takes 1 time slot for it to receive. Okay, and it sends 2 blocks to client B and sends 4 blocks to client C. Now here, client C sends 2 blocks to client A. This time it takes 2 time slots, okay, depending on the traffic. So it goes on like this. Now there is another type of edges which are very thick, and I assume that the capacity of this such an edge is equal to infinity, and what it represents is its own memory. Okay, the server, whatever it possesses at t equals 0, it passes on to itself at t equals 1. It means that you don't lose memory. Okay, so this is in fact a graph, okay, with the capacity of all these equal to infinity. Okay, so what has this to do with Avalanche? Now in Avalanche, no, for this time parameterized graph, you imagine that we're doing a random linear network coding on it. So let me get rid of all these. All right. So for client A, okay, so it receives 2 blocks from the server. It receives something from itself in the past, and then it takes random linear combinations and then send a block to client B. So for this edge, it doesn't really matter whether you do random linear combination or not, because there's infinite bandwidth. Okay? So you can assume that you don't do random linear network coding here. Okay. So in fact, this is the so what it boils down to is that in Avalanche system, it is actually doing random linear network coding on time parameterized graph. It's not doing random linear network coding on a graph that represents the physical network. Now, by examining the maximum flows in this graph, very interesting questions can be asked. For example, you can ask, when can a client receive the whole file? So you go put this, and let's say the file contains 10 blocks. Then you want to ask when will it take for client C to receive to be able to decode. So the criteria is that client C at, let's say, at a particular time needs to have enough max flow from the source node. Okay, so you just go down in time and check out when is the first time that client C would have enough max flow from the server to that node. Okay, so you can answer questions like this. You can also answer questions like if the server or some clients leave the system, can the remaining clients recover the whole file? This is something of concern all the time. And or if some blocks are lost by some clients, how does it affect the recovery of the whole file? So by analyzing this time parameterized graph, you would be able to answer these questions. So before I quit, I would like to explain a toy example to you, okay, which is an application of network coding in a network with packet loss. Now, we in this very simple network with 3 nodes, 1 packet is sent on each channel per unit time, and the packet loss rate is 0.1 on each channel. Now, by using an end-to-end fountain code, okay, this information can be transmitted from A to C at rate 0.9 square, which is equal to 0.81, because after 2 hops, the rate of packets that survive is equal to 0.81. You can use a fountain code and decode at B, and then you encode it using another fountain code. In that case, you would be able to transmit at rate 0.9, but this would incur much delay at node B, because you need to decode a whole fountain code before you can re-encode it with another fountain code. And also it incurs a lot of storage cost. Essentially, you need to buffer the whole file at the source node B at node B. Now, I claim that by using an avalanche type system, information can be transmitted from A to C at rate 0.9, which in fact is the max flow rate. You can regard this as okay. You can regard the effective capacity from here to here is 0.9, and the effective capacity from here to here being 0.9 after taking into account of the packet loss. Okay? So 0.9 is in fact the max flow from this node to this node. Why is this the case? So again, we can use the similar kind of analysis that I performed for you. So this is node A, this node B, and this node C. Okay. So you imagine that from A you transmit a packet. These are pipes. Okay, these are edges with capacity. You think of this as smaller pipes with capacity 1. Okay? And each time slot you can use one of these pipes, and occasionally with probability 0.1, this pipe can be blocked. All right, and then from B to C is the same situation, but here we also have some thick horizontal pipes, okay, with capacity infinity, like this. Now it is, well, we are concerned about the rate that the max flow grows from A to C. Okay? Now we can, it's clear that we can press water down from A to B at a rate equal to 0.9 because 10% of these pipes are blocked. It's also clear that we can press water down from B to C at rate equal to 0.9 because 10% of these are blocked. However, it's not clear that is we can actually press water down from A to C at rate equal to 0.9. It turns out to be true because of the existence of these thick pipes. So imagine that you press water down from here at rate 0.9, and then the water travels horizontally through these thick pipes, and eventually they will find their way down to level C. Okay, and at least intuitively, I can explain to you that if you consider from point A to a point here on level C, you consider max flow, and this max flow actually would grow at a rate equal to 0.9 linearly with respect to time. Okay, so because of this, as long as you have enough max flow, you would, if you apply random linear network coding in between, then you would be able to do the decoding, and that's why using an avalanche type system, you would be able to transmit information reliably at rate equal to 0.9. So I think I'm running out of time. Maybe I'll just skip to the. I just want to show you something. This is something that I've been focusing on for the past 10 years. It's something called batch sparse code or batch code, which you can think of as a efficient implementation of random linear network coding that combines the concepts of random linear network coding and quantum code. And there has been real applications of this in the smart lamppost system, and also we provide Wi-Fi services at country parks. So like this, at a country park, there's no power supply, so we have to build our own. And so if you want to probe more into this, there's a monograph that you can look into by Yeung and myself. And so this is the last slide I want to show to end the lecture. Network coding is now a very rich field of research, which has been extended in many different directions. Random linear network coding is one. Network error correction, secure network coding, I already mentioned this. Subspace coding, convolutional network coding, regenerating code originally was also an application of network coding, although for subsequent regenerating codes, they are not necessarily network coding per se. Coder caching and recently network function computation, which I'm also working a lot on with my former postdoc, Shen Guang. And there is another branch of network coding, which actually has nothing to do with the original theory of network coding. It's called physical layer network coding that applies the concept of network coding at the physical layer, namely by allowing the electromagnetic waves to add up physically. And this is the work by my colleague Song Liu and his students. It's still a very active field of research. So with this, I'll stop.
Thank you, Raymond. So participants, you have any questions, please either put on chat box or just unmute and speak up. Yeah. So yeah, think about your questions. Meanwhile, I have a few comments. So it looks very interesting, as you said, like this P2P systems or like Avalanche. So it does not. There are many problems which they apparently do not have network. But then if we see closely and model it properly in terms of time expanded or time parameters graph, then we can see that actually network coding is at play. Yeah.
Right.
And for Avalanche, it looks like as the time progresses parameter, so that way the network is built, means capacity are built are different every time.
Right.
However, the next model you described is they have fixed capacity, fixed capacities. So going from A to B and B to C node. Yeah. So I think there are many such models that perhaps hidden in a very hidden way, network coding may be playing. Yeah.
Well, I mean, even the fountain code is can be described in such a fashion.
And how do you see the functional this function network computation? So it looks like a more complicated than network coding model.
Yes, indeed. I think at this stage we are still at the stage of theoretical research because it's quite difficult. I mean, I would say that the problems are quite difficult, and it's not easy at all to obtain any exact capacity, even for very special cases. But it's a very rich problem for research.
Thank you. So any questions from participants? No questions. Okay. So thanks, Raymond, for this lecture series.
I'm very glad to do it.
Yeah. So this lecture series by you has been the backbone of this summer school program, and you have walked us through the foundational concepts, some of the most important results in information theory and network coding. And this is really very invaluable contribution to this event and the whole Indian research community. So I'm sure that for many researchers, these lectures have inspired and rejuvenated us on a journey in information theory and network coding research. And I thank you for your generosity. And we again congratulate you on the Shannon Award and the Shannon Lecture next Thursday, coming next Thursday.
Oh, thank you very much.
Thank you, Raymond. So you have any concluding thoughts?
Well, I mean, it's a pity that I cannot travel to attend this summer school in person, which I hope to be able to do so in the future. And
Yeah,
at the same time, I would like to invite every one of you to visit Hong Kong at some point. When we are hoping that this will become possible soon, because in Hong Kong we're actually opening up gradually.
yeah. Thanks a lot, Raymond.
Yeah. Well, it's nice to see you.
Nice to see you too. Yeah, and I really want to come visit you, and of course I want to invite you all. So I'm very hopeful that in near future we'll have a really good event, fruitful event. Yeah.
Very good.
Thank you, Raymond.
Okay, thank you very much. Bye-bye.